the time bandwidth product can never be less than 1/4, 0.25. So, 0.25 is the very lowest value of the time bandwidth product that you can get. And what we have concluded here has nothing to do with the tools available at a particular time, with the technology available at a particular time, or with the machines and the political situation or whatever. It is fundamental to signal processing. In fact, so fundamental is this result that we have derived, that in different manifestations it is seen in different subjects. What we call the uncertainty limit in physics is just another version of this. People talk about the inability to locate position and momentum simultaneously. Actually, it is just another version of this. I shall just give a small hint as to how you might connect this idea of time bandwidth product to the concept of position momentum uncertainty. And to do that, actually we will go back to the expression for the time bandwidth product that we had derived. You see, you notice that we have shown that essentially the time bandwidth product relates to a time variance, the time variance relating to the norm of t x t the whole squared. And you are assuming the object is centered. So, now think of x t as descriptive of an object. Remember that we had talked about a one dimensional mass. Now, here we are talking about x t then as a kind of mass distribution of the object, or rather if not mod, if not x t, it is really mod x t squared, which is like a mass distribution of that object. So, division, the denominator part is essentially a normalization, make the object unit mass if you like. But here in the time variance, the numerator is indicative of the uncertainty in position. What is the variance of the object as far as its spread around the center is concerned? That is what the time variance tells you. Now, if you look at the other term there, the frequency variance. So, time variance involves this, frequency variance involves this. And involving this, the derivative of x t with respect to t. Now, x t or mod x t squared, as I said, is indicative of, in some sense, the presence of that mass or that body on t. So, dx t dt is indicative of the movement of that body, the change with respect to time. So, here in some sense a change, it is indicative of a change. So, in a broad sense you can see the connection between position and momentum, uncertainty in where it is and uncertainty in how it changes. Let me not dwell too much further on this. To interpret precisely how this is the uncertainty principle in physics, I think we should leave it to a physicist, a person who specializes in that, but this is what I have just given you is an intuitive indication, that is all. However, it is just to bring out the various meanings that this time bandwidth product or this uncertainty limit has. It has meanings in different subjects. Anyway, coming back to a subject with which we are dealing, this is the whole basis of the subject of wavelets, or for that matter time frequency methods. What it tells us is that no matter what we do, we are not going to get any function which has finite energy and which can be confined beyond a certain point in the two domains, time and frequency, simultaneously. That is bad news. What was worse is that if you looked at the Haar case, it is not confined at all, that time bandwidth product was infinity. So, now we naturally ask the next question, is there a function which gives us this 0.25, or is it something that we should never seek? That is not very difficult to answer. In fact, that can be answered again by using a vectorial interpretation. When does the numerator become equal in the Cauchy-Schwarz inequality to the expression that we derived? So, the optimal function in the sense of time bandwidth product means the Cauchy-Schwarz inequality becomes an equality. Now, when would that become an equality? It would become an equality if the cos squared theta term is 1. That is, the cos squared theta term is 1. And what do you mean by the cos squared theta term being 1? What really is theta? Theta is an angle between these two so called vectors, t x t and d x t dt. If you want the angle to be such that cos squared is 1, these two vectors must be collinear. They must be along the same line, so to speak. So, therefore, in the language of functions, we need the vectors, so called vectors t x t and d x t dt to be collinear. One dimensional. What do you mean by them being collinear? They must be linearly dependent. And what do you mean by them being linearly dependent? Any of them must be a multiple of the other. So, in other words, dxt dt is some constant. Let us call that constant gamma 0 times t x t. The solution of this equation would give us the so called optimal function. So, we solve this. How do we solve it? By a simple change of the or this redistribution of the derivative. So, essentially what we are saying is dx by x is equal to gamma naught t dt, and if we integrate, we get gamma 0 t squared by 2 or log natural x. Well, you must have a constant here, a constant of integration. And this is of course log natural x. So, in other words, we have log natural x is of the form gamma 0 t squared by 2 plus C 0. Let us raise both sides using the natural base e. So, e raised to the power ln x is e raised to the power this, and therefore, we have e raised to the power ln x is just x. So, x of t is some constant e raised to the power C 0, this is a constant. Let us call this constant C 0 tilde times e raised to the power gamma 0 t squared by 2. So, let us write that down again, and let us make a remark on gamma 0. X t is of the form C 0 tilde times e raised to the power gamma 0 t squared by 2. Now, you want x t to belong to L 2 R, and therefore, you want mod x t squared, which is essentially mod C 0 tilde squared times mod e raised to the power gamma 0 t squared by 2 to be integrable. Now, this is possible only if gamma 0 has a negative real part. If gamma 0 has a positive real part, this is going to be a so called Gaussian that grows in time. It is not going to be square integrable, and therefore, we must choose gamma 0 with a negative real part, and we can choose any one example of that. So, in other words, one function which reaches the lower bound, which is optimal in this sense, is with gamma 0 equal to minus 1. And there we can also choose, of course, C 0 tilde to be 1, because it does not matter if you scale a function, the time bandwidth product is unaffected, and therefore, one optimal function in the sense of time bandwidth product, that is with time bandwidth product equal to 0.25 is the Gaussian. A very interesting conclusion. The Gaussian is optimal. The Gaussian seems to arise in many situations. It has arisen in this. Having noted this, we shall conclude today's lecture and proceed in the next lecture to delve further into this issue of how close we can get to the optimal with other functions. Thank you.